Okay, welcome back to this final day of the conference. I'm very glad to have the opportunity to introduce you Marco Pozzetta from Politecnico di Milano, who's going to speak about quantitative isoperimetric inequalities in capillarity problems. Please.
Thank you. Thank you very much for the introduction. Thanks to the organizers for the invitation. I'm always very happy to be here to give a talk. Okay, so I will speak about a very recent work in collaboration with Davide Carazzato and Giulio Pascale. Davide Carazzato is now a postdoc at the University of Vienna, while Giulio Pascale is a postdoc at the University of Naples, Federico II. And if you want, the preprint of our work appeared today on Archive, if you are curious about details. Okay, so I will speak about quantitative isoperimetric inequalities. So I will start with a gentle introduction to quantitative isoperimetric inequalities, and then I will move to our work. Okay, so let me begin with the case of the classical perimeter. So I want to state a theorem to remind you what the topic is about. So classical perimeter. So consider a set E contained in Rn, set of finite perimeters. Set of finite perimeter. And for simplicity, I will always assume that the volume of a set, I denote it like that, is going to be equal to the volume of a unit ball in Rn. So I'm normalizing the volume. Okay. Then you know for sure, so I want to state a list of conclusions. And for sure you know that the ball is a solution to the isoperimetric problem. So if you fix the volume, the perimeter of the ball is less than the perimeter of E, right? So you can write the sharp and rigid classical isoperimetric inequality in Rn, which and I'm going to state it like this, like 0 less than perimeter of E minus perimeter of the ball, right? Which is what I said, perimeter of E greater than perimeter of B1, okay. The inequality is sharp, is rigid in the sense that equality holds if and only if E is a ball. And I wrote it like this because it is more similar to what it is a quantitative isoperimetric inequality. Because on the right-hand side, we have what we call the isoperimetric deficit, which is telling me, what is the difference in energy between my competitor and the minimum of the problem. And on the right-hand side, I have 0, of course. Turning this inequality into a quantitative inequality means to put the deficit, for example, on the right-hand side, while on the left-hand side, you would like to replace 0, so you want to erase 0, you want to delete it, and you want to put here some asymmetry index. Asymmetry index. Now I will give you an example, but basically you want to replace 0 with a positive quantity. So you get an improvement on the inequality, right? Something greater than 0, no, something greater than something positive, which of course has to vanish when E is equal to the ball. Okay, so the example, before arriving to the main example, let me tell you if a very important but partial result is the so-called Fouglede inequality. It is already going to be a quantitative inequality. So it's inequality proved by Fouglede in 89, and it states the following. So it's going to be a quantitative inequality in a particular case. The particular case is the following. Consider, I will just draw a picture. Consider the following case. This is B1, so this is the ball. And my competitor E is going to be a small C1 perturbation of the ball. Small C1 perturbation means the following, right? This is a C1 perturbation. So you have a normal graph by a function u defined on the sphere, u on Sn minus 1 into R, C1, very small C1 perturbation, right? Okay, u is C1. And also for simplicity, let me assume here that even if you are moving a little bit B1 into the new set E, let me assume that the barycenter is still the origin, just like the ball. So under these assumptions, if the C1 norm of U is less than a dimensional constant, epsilon n, positive, but very little, then you have a quantitative inequality. The quantitative inequality states that the H1 norm squared of U is less than up to constant. Okay, whenever I use this symbol, I mean that there is some constant which doesn't depend on anything important. So for example, a dimensional constant in this case, right? Okay, so this is less than isoperimetric deficit, PE minus P B1. Right. So you see, this is what I meant. This is measuring in a quantitative way how E is different from B1. And indeed, when the deficit is 0, U is 0, and you are back to the ball. But in general, you improved. You improved the inequality above in a quantitative way. Okay. So of course, this holds only for a little perturbation of the ball. So for almost 20 years, people ask themselves if you can improve this to sets of finite perimeter. And finally, this was proved by Fusco, Maggi, and Pratelli. Maggi and Pratelli in 2008. By proving the following quantitative inequality, where the asymmetry is the following. It is the so-called Frankel asymmetry. Frankel asymmetry. It is the following. You take E symmetric difference with B1 centered at some point x naught, infimum over x naught in Rn. Okay, so you see, possibly moving the center of a ball, you are looking for the ball which best approximates E in an L1 sense, right? Okay, you square it, and this is controlled once again by the isoperimetric deficit PE minus P B1, and you improve the inequality to the class of set of finite perimeter, right? And this is the first instance of a sharp inequality. Also, Fugletti's inequality is sharp, and this is the first instance, the first proof of a sharp quantitative inequalities. In this context, what does it mean? What does it mean sharp? It doesn't mean that the constant here is sharp. The constant here is something very, uncontrolled. Okay, dimensional constant, but sometimes you don't even compute it. When you say it is sharp, you mean that it is the exponents are sharp as the deficit goes to 0. Okay, right? So as the deficit goes to 0, this goes to 0, meaning that this is sharp. It means that, for example, this 2 here cannot be turned into a lower exponent in this case, right? For example, not the power 1, okay? Which would be much greater, right, when the deficit goes to 0. Okay, so it is sharp. And now you see, here comes the question. You see, okay, the second inequality is stated in the class of sets of finite perimeter, while the first one is in a more restrictive class. But if E is a C1 perturbation, the Fugletti inequality is much more precise than the second inequality, right? Because this is just an L1 distance, while this is an H1 norm for the function U. So this is much more, is a higher order distance, right, from the ball for the set E, okay? And so you have this spontaneous question, okay, but we have this nice inequality, but we know that in a particular case you have you can bound with the deficit, you can bound a higher order distance from the set of minimizers. So you ask yourself, can we do something similar in the setting of set of finite perimeter? Can I replace the Frankel asymmetry with a higher order distance from the set of minimizers? And the answer turns out to be yes. This is the final result I want to mention in this context. It is a more recent result by Fusco and Yulin. Fusco Yulin in 2014. And it states the following. So on the right-hand side, we're always going to have the isoperimetric deficit. And on the left-hand side, we have the following quantity. I'm going to call it beta. Beta of E. Beta of E is, it's going to be again an infimum, because among all possible, you want to translate all possible balls until you get the least, the maximal superposition possible. So it's not surprising I have an inf over x naught in Rn. It's going to select the best center, right? And then I'm going to tell you an asymmetry that is higher order with respect to the Frankel one. It is the following. Let me first write it. You integrate over the boundary of E, if you want to be precise, the reduced boundary of E, because now it is just a set of finite perimeter. And you look at this difference. Nu E at x minus x naught over x minus x naught squared. And this is bounded by dimensional constant times PE minus PB1. All right. So let's give a look at this. Nu E for a set of finite perimeter is the generalized outer normal in my convention. Okay. And you see, I am measuring the deviation between the sort of L1, L2 distance, in some sense, between the normal of my set E and the spontaneous normal of a ball, right? This is a sort of oscillation asymmetry. And in some sense, this is well, you can prove that it is stronger than the previous one, and in some sense, this answers my question, right? Because in the set of finite perimeter, now, yes, I am estimating an asymmetry that is of higher order with respect to the Frankel one, right? Because I have normals, right? Now it is more similar to the H1 norm of the graph function I had before. All right, and now in my talk, our aim will be exactly to study this second kind of inequalities. Then they go under the name of strong form. So the second type of inequality is a so-called strong form in the literature of the quantitative isoperimetric inequality. So when I say strong form, I mean that I want to bound from above some higher order asymmetry. All right. Okay, and the story about strong forms of isoperimetric inequalities is much more limited. I mean, it's quite somehow a new topic, I would say, in the sense that I am aware of only 2 more works where you have a strong form of isoperimetric inequality, and I want to talk about these other strong quantitative inequalities. They are in the setting of anisotropic perimeter. Anisotropic perimeters. In this setting. So let me just briefly remind you what it is. An anisotropic perimeter. An anisotropic perimeter is a functional of this form. You no longer have the perimeter, you have a perimeter depending on a function f. The perimeter of a set is defined as the integral over the reduced boundary, as always, of a function of the normal, right? If my function were the norm, the modulus, you just get 1, you get the measure of the reduced boundary, you get the classical perimeter, right? While in general, f is one homogeneous convex function, okay? It's a norm, basically. You can think of f as a norm, okay, in Rn, but possibly different from the Euclidean norm, of course. Okay, so this is an isotropic perimeter. There are several ways to present this, so for sure, so maybe they are all equivalent, so maybe this is not what you used to, but it's all equivalent. If you define the anisotropic perimeter like that, then you define the dual norm. The dual norm, of course, at x is the supremum of scalar product x, y among y's having norm less than 1. Okay, and then you define the so-called Wolf shape, k. My Wolf shape is the unit ball. Is the unit ball with respect to the dual norm. Okay. Think if f were the modulus, k would be the Euclidean ball. Okay. And indeed, k, the so-called Wolf shape, is going to be the isoperimetric set for the anisotropic perimeter. It's very spontaneous, very classical, and then you can ask yourself about quantitative isoperimetric inequalities. So now the theorem goes like that: take E in Rn, again, set of finite perimeter, as always, don't make me write it. I fix the volume to be equal to that of the Wolf shape, and then you have a list of conclusions. So first conclusion, I could state, I don't want to, the very same isoperimetric inequality, which is again sharp and rigid, so perimeter of E minus perimeter of K, now anisotropic, greater or equal than 0. I want to turn it into a quantitative estimate. And for example, this is the celebrated work by Figalli, Maggi, and Pratelli, right, from 2010. They have the version the sharp version for the Frankel asymmetry with respect to translations of the Wolf shape, right? And so they have the analog of Fusco, Maggi, Pratelli for the anisotropic perimeters. But as I told you, I'm interested in the stronger form, the strong form of quantitative inequalities. And as I told you, I am only aware of a couple of works. The first work is a very nice paper by Robin Neumayer from 2016, and it states the following. So now, similarly as before, I'm going to have an oscillation asymmetry, and now the oscillation asymmetry beta is going to depend on f, my anisotropy, of course, and this is going to be a little bit different from this one in terms of figuring it out in your mind. So the definition is the following: Bf of E is defined as, again, I need an infimum over translations. I have an infimum over possible centers, integral over the reduced boundary of E of, and the asymmetry she chose is the following: f of nu e minus scalar product nu e at x, so everything is evaluated at x minus x naught over f star x minus x naught, like that. Like that. Now I need to raise everything to some power, and this is controlled up to dimensional constant by pf of e minus pf. Okay, now let's first have a look at this. It's not finished yet, this inequality, but let's have a look at this inequality. You see, the oscillation asymmetry seems different. I will claim that it is not, but seems different. For sure, my oscillation asymmetry here is not difference between normals. That is not different. You cannot rewrite it as nu e minus normal of the Wolf shape. You cannot do that. Nevertheless, I will claim that they are very similar in a minute. And a second observation, what is inside here is non-negative by the differential inequality. Okay, so differential inequality in convex analysis tells you that this is non-negative, and you can prove it is zero if and only if E is a Wolf shape. I mean, you can do all these lemmas and actually prove that you have an oscillation asymmetry. And right, so okay, we accept it. And the important thing is that you need to raise this quantity to the power 2n over n plus 1 if you don't want to assume anything. And it is not clear whether this is sharp, so it is still an open question whether you can prove without additional assumptions, whether you can prove this with exponent 1. But okay, you can replace this with exponent 1 if, you know, my Wolf shape is at least C2 strictly convex, you know, with adding some strictly convex, you know, if you add some regularity assumptions that make the anisotropy more friendly, then you can actually replace that to the power 1, like here. Beta is raised to power 1 in this other inequality. And in that case, it is sharp. Okay, good. Now, before commenting more on this kind of oscillation asymmetry, let me state also the second. I told you I had two works to mention, and the second work is a more recent, very nice work by Kenneth de Maison. So de Maison from last year, and he proved the sharp version of this inequality in case the Wolf shape is exactly a crystal, okay? So completely opposite framework with respect to the C2 strictly convex assumptions here, right? Okay, so completely opposite. So if you assume that that the norm is crystalline, if you want, so the K is a crystal, what does it mean? Crystal, it means it's a finite intersection of half spaces, okay, like a cube, I don't know, okay? If it is a crystal, then he managed to prove that beta f e is less than. Okay, here is a bit different, so I'm going to be precise. You have a constant depending on the dimension and on k times the isoperimetric deficit, so pf e minus pf k. Okay, so it's a bit different, fine, but at least the exponent is 1, and it is a sharp one. Okay. So, and the study for the moment, as far as I know, stops here about this strong form of inequalities. And I want to conclude this presentation with a little remark that will be very important for later. The remark is the following. I claimed that even if it doesn't seem so, beta and beta f are very similar. I claimed so. And in which sense they are similar? In the following sense. You can rewrite them in a common way. The common way is the following, and this will be relevant for later. Both beta or beta f of a set, both of them, you can rewrite them, you know, expanding square using the divergence theorem and so on. You can rewrite them as your perimeter functional applied to E plus a volume term. So let me just say like this, like the integral over E of some integrand, so volume term, okay? And this is very nice news if you already know the proof, okay? You can rewrite your oscillation as a volume perturbation of the perimeter you are studying. This is going to be relevant in the sequel, okay? So your perimeter plus the integral. In the case of the isotropic perimeter, here you get minus n minus 1 over modulus of x. So very nice function, 1 over x, basically. Okay. I will come back on this remark later. Okay, so now we are ready to I'm ready to tell you about our setting. The setting is the capillarity setting. Capillarity problem. Capillarity problem is the following. So let me begin with definition. So from now on, I will fix a parameter lambda between -1 and 1, okay? And maybe you already know about the capillarity perimeter. I am considering the most classical capillarity perimeter. It is the following. You take, let me go here. You take a set E. E is going to be contained in H. For me, H is going to be xn greater or equal than 0. So you consider sets in a half space. Let's consider the upper half space. Okay. I will also call H plus the interior, so xn greater than 0. Okay, it will be useful in a minute. And the notion of perimeter you consider is the following perimeter. You are going to count all the interface of the of E, but you're going to put two constant different weights. You put a weight 1 for the interface between the set and the air, okay? And you're going to put a weight minus lambda. I'm sorry, that is the common convention. Not lambda, but minus lambda for the contact part of your set with the substrate, I don't know, with the boundary of the half space, okay? So your capillarity perimeter is going to be dependent of this on this parameter. P lambda of E is going to be the perimeter of E inside H plus minus lambda, the perimeter of E in the boundary of H, if you want. Okay. So easy to remember. That's the capillarity perimeter. Okay, a little remark. Of course, you can fix the volume, you can minimize P lambda, you look for isoperimetric sets. So it is very classical, well known that you have isoperimetric sets, and isoperimetric sets, so the analog of unit ball or the analog of wolf shape in this case are suitable truncation of balls. So let me do this picture. Depending on the sign of lambda, it's going to be more or less convenient to touch the boundary more or less, right? Okay. So in the case lambda is positive, you see this picture. Lambda positive. In the case lambda is negative, you're going to see a bubble like that. Lambda negative. Lambda 0, you get exactly 90 degrees, okay? So these are the pictures. Let me be more precise. What I'm drawing here is the case where this is a part of a Euclidean ball of radius 1, whose center is outside the half space. The center is going to be minus lambda En, okay, minus lambda En, and you have the same here, but lambda is negative, okay. So this center, this is again radius 1, but the center is again minus lambda En, but lambda is negative, right? So you go up. And so in particular, I told you I want to talk about strong, yeah. No, exactly. No, the volume is not equal to 1. This is my reference model, if you want. This is my reference model. Also for the wolf shape, you don't know a priori how much is the volume, but that is your reference isoperimetric set. So here I will, in this case, I work with sets having fixed volume equal to B1, their volume fixed to K. Here, volume of set is going to be equal to the volume of this one, or that one. Okay. In both cases, I will call these models the bubbles B lambda. And that is my model, just like a wolf shape, and so on. So this is my B lambda. And as I told you, I want to work with strong forms of isoperimetric inequalities. So let me just observe how you compute the outward unit normal of the model. What is that vector? This, so if this point is x, this vector here, now it is just x minus 0 minus lambda, right? Minus 0 minus lambda over x minus 0 minus lambda. So this is maybe not very nice to see, but this is just the unit normal, outer unit normal you see on the outer interface. All right. And so now I'm ready to state the theorem. So our theorem, so in collaboration with Davide Carazzato and Giulio Pascale, appeared today. is the following theory. It's exactly what you expect. By the way, maybe before telling you this, let me just say that the Frankel version. So you can imagine in your mind a Frankel version, right? For also this perimeter. Okay, this is already known, and it was proved independently actually by me and Giulio Pascale, and independently by Kreutz and Schmidt last year. They also have the anisotropic version actually. So. Check it out. And today we have the stronger version. The stronger version is the following. Now, to distinguish, I will call mu our oscillation asymmetry. And our mu is going to be infimum over... Now, you know, the spontaneous translations are translation along the boundary of H. The problem is invariant with respect to translation. So my infimum, so the centers are moving only over the boundary of H. It is reasonable to center, recentering only with respect to the boundary of H. So you have infimum with respect to that of exactly, so it's not nice to see, but it's clear what's going on. You integrate over interface intersection with H plus, so you're only measuring the difference of the oscillation over there, otherwise the normal is constant. And you have nu of E evaluated at x minus x minus a translation of that, so x naught minus lambda over x minus x naught minus lambda modulus raised to power 2, bounded by a constant depending on the dimension and on lambda, but lambda is fixed, times the isoperimetric deficit, which is p lambda of E minus p lambda of b lambda. Of course, I forgot to mention that, as I told you, I am fixing the volume to be equal to b lambda. Of course, you can always produce scale invariant versions of these inequalities, right? And this is for any set of finite perimeter where having that volume. Okay, so this is our main result, and now we look at this asymmetry. I called the whole asymmetry mu, and let me use another symbol because it's going to be useful. The quantity I'm taking the infimum of is depending on x naught. I'm going to call it mu x naught. So mu is the infimum over x naught of mu x naught, right? Okay, so mu x naught of E. All right, now you see the oscillation asymmetry. By the way, the exponents are sharp. You can check with an example, and you can see immediately that apparently our oscillation asymmetry is very similar to the spontaneous asymmetry you want to see in the case you see in Fusco-Yulin's work, and so nice. But okay, and now I don't know, maybe you might be thinking, oh, nice. So you did the adaptation of the original result. This is fair. You have a question? Oh, no, okay. So you did the adaptation, maybe, or the adaptation. Well, it is not. I want to convince you that this is not the adaptation of the adaptation. Already, their work is not the adaptation of Fusco-Yulin, because in all cases you have new troubles to face. Okay. In particular, I would like to point out two troubles you have in proving this inequality. One trouble is in common with that Neumeier had. And so it is already different from Fusco-Yulin, but we have to face a second trouble. And the reason is that, the ultimate is going to be a bit technical, this comment, but the ultimate reason is that even if you look at this oscillation, and it seems very similar to that, the nature of this asymmetry is very different, because in our case, you cannot rewrite mu in this form. You cannot rewrite mu in this form. So my remark is the following. Let me write it here. So my remark, to compare, my remark is the following. I want to observe this both for mu x naught of a set and both for mu. You try to do a similar computation, you expand the square, you do the divergence theorem. You would like to see the perimeter you are studying plus a volume term, and you can do that, plus vol term, but the expansion goes on. And you have, and unfortunately that's the true problem, you have a further integral, which is not a volume integral, it's an integral over the boundary. It's an integral over the boundary of a weird quantity, depending on x naught, of course, depending on x naught. So even if I don't want to tell you what it is the expression, the point is that it's not a volume perturbation of your perimeter. It's a perimeter perturbation of your perimeter, which is bad for regularity theory, right? That's the point. And even worse, this is mu x naught. If you take mu, you're going to take an infimum over x naught. And that infimum is going to depend on the set E, of course, because it's the best center for E. So after you take the infimum, if you really want to see the expression as some perimeter plus volume, that you are going to end up seeing a perimeter that is anisotropic, but with an anisotropy depending on E. And this is very bad. So if you really want to rewrite it like perimeter plus volume, you can do it, of course. You can do it. You can just sum these two integrals over the boundary. You call it a new perimeter, okay? But you're going to end up with a perimeter depending on the set. So and it's not really a functional over sets. I mean, or if you want, it is, but this is what you will see. And this makes the problem much different from a technical point of view, I have to say. From a technical point of view, it's going to be very different from the previous situations. All right. So as I told you, I want to convince you. I want to, I want to explain why this causes many troubles. And so now we'll move to the proof. Okay, a sketch of the proof to explain why this makes things different. All right. So okay, maybe I will keep the classical perimeter case on the board to compare. Okay, you will remember this remark, okay, because we have the other one. And I am erasing this blackboard because to tell you about the proof, I first need to tell you something about the proof of the very classical perimeter, So a very quick sketch of the most classical case. So there are many proofs now of the quantitative versions of the isoperimetric inequality in the classical perimeter. And I want to maybe you already know about this. I want to remind you about a very robust strategy that is called the selection principle. It goes under the name in the literature. It is called the selection principle. So I want to briefly describe this so-called selection principle. Now, the selection principle is an amazing idea that Cicalese-Leonardi had. Leonardi had in a paper in 2012. And let me also mention there is more or less a contemporary work with very similar ideas by Acerbi, Fusco Morini. So I would say this selection idea was performed in these two works. And it turns out that it is a very clever, very robust strategy. It has been used many times to prove many different quantitative isoperimetric inequalities. And the basic strategy is the following. I will say that it is divided into, people usually say that it is divided into 2 points, into 2 steps. I will say that you have 3 steps in the classical proofs, okay? So the first step, the usual first step in the selection principle is that you need to check that you have a Fuglede type inequality. Okay, first step, you need Fuglede. And you are lucky because Fuglede in the past you already proved a Fuglede type inequality, right? Fuglede type inequality is an inequality sharp quantitative for C1 perturbation of the problem you are studying. Okay, so you need Fuglede. So Fuglede, you have Fuglede, right? Second step. After you prove the Fuglede step or you ask Fuglede, the second step, which is sometimes you can skip the second step when you present this, but this I will tell you because it is different with respect to our case. Then from the Fuglede, you want to prove the inequality in the realm of sets of finite perimeter. Right now, you want to deduce that you have the inequality on the sets of finite perimeter. Well, there is a nice second step that is a technical lemma telling you that many times it is enough to consider sets of finite perimeter that are uniformly bounded, that are inside some ball. This is a confinement reduction. Okay, you just observe that if your set is too spread, then you can truncate it, and if you prove the inequality, the quantitative one for the truncation, then you have the inequality for the other set. So basically, it's a technical lemma that allows you to do this reduction to uniformly bounded sets, okay? Confinement reduction, okay? And this is based on the nature of the problem you are studying. And then you move to the third step, which is the most important one. It is the actual step you would call selection principle. And the proof goes by contradiction. By contradiction, in this case, by contradiction, what do? You say, okay, by contradiction, let's say I'm going to prove what I'm going to prove. For example, a sketch of Fusco-Yulin proof. Okay, so by contradiction, let's say that I have a sequence of sets having the correct volume. By exploiting 2 without loss of generality, I can consider EK inside BR, but they are violating the quantitative isoperimetric inequality, which means beta of EK is greater than K deficit perimeter of EK minus perimeter of B1. I am exactly negating exist a constant such that, so now for any constant exists a counterexample. And I have my negation. And the idea is, now, these are just sets of finite perimeter, but if by any chance EK were a C1 perturbation, you already get a contradiction, right? Because I already have the Fugglede step. Okay, so if by any chance EK were a C1 perturbation of the ball, that is impossible, all right? And so you want to go back to this case. You want to regularize EK. If you're able to regularize EK into a C1 perturbation of the ball, which is still satisfying the absurd assumption, then you get a contradiction. You want to regularize EK. And how do you regularize? By solving a minimization problem, right? Because solutions to minimize sets that minimize something many times are nicer than random sets, right? So this is the idea. You're going to take Fk, a new set, which is going to be a minimizer of, and the usual problem, there are many versions, but it's something like that. You pick a set contained in BR, because I can work here with uniformly bounded sets. You pick a set and you minimize something that is usually something like that. Perimeter plus a volume term, which is E minus B1, and then I will add something that is, in this case, minus 1 over K, minus 1 over K beta of E. And this is my functional. This is my function. Now let's have a look at it. This is a functional, of course. You see, it is perimeter plus volume term minus constant times the asymmetry index I am studying. Beta is the asymmetry index I am studying. Okay. Now, if you think that K is very large, if you forget about the last term, if you forget K very large, forget about the last term, you can just get perimeter plus a term that tells me it is convenient for the volume of E to be similar to the volume of B1, okay? Because otherwise you just get the empty set, right? Okay. And indeed you can check that if you erase the last term, if lambda is sufficiently big, the only minimizer of the first two summands is the unit ball. So you see, as K goes to plus infinity, this disappears, and so you are approximating a minimization problem that is only solved by the ball. So you expect that Fk for K large is going to be similar to the ball, which is what you want if you want to apply Fugglede. Okay. And so you put a term that is only minimized by the ball, but then you subtract something that favors being a bit different from the ball, right? This is happy, there's a minus in front, so this is happy if the asymmetry is big, okay? And so Fk is not going to be the ball, but it's going to be close to the ball, possibly. And in fact, you can do, you can check that, you can do this rigorously. And doing a couple of computations, very easy, I don't want to write them. You do two observations. So first observation, there exists a minimizer just by direct method because you take a minimizing sequence, which is uniformly bounded. It's going to converge somewhere. You get a minimizer. So Fk exists thanks to point 2. And then you do a couple of estimates, and you discover that Fk still is contradicting. So beta F, just by testing the functional on Fk with respect to Ek, you discover that beta Fk, again, is greater than K perimeter of Fk minus perimeter of B1. So Fk is still contradicting the inequality as you wanted. Second observation, you can rigorously prove what I said before. Since the functional is a perturbation of a functional only minimized by the ball, as K goes to plus infinity, at least Fk is going in L1 to the unit ball. You can prove this, all right? And you're not done yet, okay? Now you have a contradicting sequence of sets which are similar to the ball, but similar only in L1. If you want to apply Fugglede, you need similar in C1, but then you apply an epsilon regularity theorem, right? So the classical epsilon regularity theorem is telling me that whenever you have, roughly, when you have a minimizer of perimeter plus volume term, and this is a volume term, because you remember the remark I had before? Beta E is perimeter plus volume term. So perimeter, you sum with the other perimeter, you have perimeter, and the other is a volume term. So here you have a volume perturbation of the perimeter. You can apply an epsilon regularity theorem telling me that such a minimizer, whenever is L1 close to the ball, then it is in fact C1 alpha close to the ball. All right. So this convergence implies that Fk goes in C1 to the ball, and then you have your contradiction, right? Because eventually you're going to have a set very similar to the ball, contradicting, and then contradict the inequality, which contradicts Fuglede. Right. Okay, and this is the main principle, main sketch. And now I want to tell you something. I'm going to erase the remark. We remember this, that our oscillation is not perimeter plus volume, okay? And I will tell you something about our case now in comparison to that case. So proof of our theorem, sketch of the proof. Sketch of the proof is the following. You want to mimic the 3 steps, right? You read the papers and you try to adapt and you discover that everything goes wrong. First observation, you want to do the Fuglede step. So you want to take a little perturbation of your bubble, and you want to prove a quantitative inequality. How do you do? You cannot do a normal perturbation here. If you do a normal perturbation, you don't get a competitor. Okay, but it's not that difficult actually. You have many ways to do this. For example, if this is my bubble and this is another set, which is not a normal perturbation, well, but you can write both of the sets as C1 graph over a half sphere, because the half sphere has the normal, which is tangential to the boundary of H when you reach the boundary. Okay, so you can parameterize both as a graph, and you can say a C1 perturbation is a C1 perturbation of the graph parameterizing the bubble, all right? So it's not very difficult. Call it U, the perturbation. You want to do the Fuglede estimate, and you discover that you cannot adapt the Fuglede's proof, okay? And this is the first trouble that we have in common with the Neumayer work, okay? Why can't you do this? Because if you know about the Fuglede's proof is very delicate, actually, very delicate, because this proof builds on knowing exactly the behavior of eigenvalues of the Laplacian over the sphere. This is very delicate. And you don't have a sphere here, just like Neumayer doesn't have a sphere because she has a wolf shape. It's not a sphere. And so you cannot do the same proof. Luckily, you can adapt Neumeyer's proof. So I don't want to, now I will not stress. Let's just say that after Neumayer, we can do something similar here. The computation is just more involved a little bit. But you can prove that if that function U has C1 norm less than epsilon, depending on n lambda, you do have a version of a Fuglede type inequality. My Fuglede type inequality is going to be U H1 norm squared less than up to constant, isoperimetric deficit, P lambda E minus P lambda B lambda. And if you don't want to fix the barycenter, you also get a barycenter here. So plus barycenter of E squared, where, you know, what is barycenter? Partial HE is just the barycenter of the projection of E over boundary of H, because those are the translating dimensions, right? Those are all right. So you do, okay, you adapt Neumayer, and the first trouble is solved thanks to her work. Okay, now you move to second step. You move to second step, and you would like to do a confinement procedure. And maybe it is true, but we were not able to do step 2, simply, okay? Why so? Exactly because of the remark I pointed out before, because in the classical cases, the confinement procedure relies exactly on the expansion of the oscillational symmetry as perimeter plus radial weight integrator over the set. So the radial weight is very important. In our case, you don't have that expansion. So I mean, maybe it's true, the confinement procedure, but we were not able to prove it. So what do you do when you cannot prove it? You just skip item 2, and you try to prove item 3 in any case, right? So you skip, so you don't have confinement procedure, and you skip it, and you move to item 3, and you try to see what you can do. And so you argue by contradiction. By contradiction, you take your sequence EK having volume of B lambda, Without lots of generality, you fix the barycenter of EK to be the origin, the origin in the boundary of H, for example. And this is contradicting, okay? This is contradicting. Okay, for simplicity, let me write mu0 here, okay? I will, if you want, I can comment on that later. Mu0 E, this is greater than K P lambda EK minus P lambda B lambda, right? Okay. If you know, here I am negating the inequality with mu0, okay, which is a negation that is stronger than the other one, okay. But just think that I am arguing by contradiction. I'm taking a sequence of sets. I'm translating them to have zero barycenter, and I am negating the quantitative inequality. What do you do now? The important point is, what do you do now? Again, you want to regularize EK. If you can regularize them in order to get the C1 perturbation of the bubble, then maybe you can apply the first step in any case. So you try to set up a minimization problem. The minimization problem you set up is going to be P lambda of E plus capital lambda, something that is trying to fix the volume, to be similar to that of the bubble. Then you subtract, just like before, minus 1 over K, the asymmetry you are considering, mu0 of E, right. Then I leave some space. But since we don't have step 2, we cannot restrict to sets inside some ball. So you just minimize this among sets contained in H with a finite measure, but they can be unbounded, they can move, they can translate anywhere, okay? If you want to try to rule out this translation invariant, here maybe you add a penalization to that. That is the barycentric penalization. Barycenter, boundary of H of E squared, okay? And still you have a couple of complications, right? The first complication is that you don't have a confinement procedure. So if you take a minimizing sequence that could move away in principle, it's not clear you have existence of minimizers in this case. And the second complication is that I told you, the one I told you is related to what I told you before. Here, I cannot put mu. I need to put mu0. Why so? Because you remember, if I put mu, then mu is not equal to perimeter plus volume term. It's going to be equal to a perimeter depending on the competitor plus a volume term. And in that case, as far as I know, there is no hope then to use a regularity theory for perimeter almost minimizers, right? Because even if you have a minimizer for that infimum, that is not going to be a and if you put mu, then you don't get a minimizer of something, of a functional that is perimeter plus volume, but is a minimizer of a perimeter depending on the competitor plus volume. And so you're not minimizing a fixed functional, basically. You're minimizing a functional depending on the sets. I mean, I don't know if you have a regularity theory for that. And so this is why you put mu0, because at least mu0 is going to be expanded in a fixed functional perimeter, which is still not P lambda. All right. And so how do you solve these troubles? So we combine this, I think it's a new idea, to combine this selection type principle in order to get first existence of minimizer, to combine it with Ekeland variational principle. Because if you apply Ekeland variational principle on the complete metric space, which is the upper half space endowed with the L1 distance, if you apply it, at least you can say that you have, for any j, you have some minimizers ej that are minimizers not minimizing your first functional. Let me give a name to this functional here. This is going to be fk. Maybe you don't have at first a minimizer for fk, but you have a minimizer for a perturbation of fk. And the perturbation is the following. For any j, you have ej such that fk ej is less than fk e plus 1 over j, ej symmetric difference with e for any e. Ekeland tells me that, okay, maybe you don't have a minimizer for your original functional, but as long as your functional is bounded from below, lower semi-continuous on a complete metric space, then at least you have a minimizer for functional plus distance from that set. You see? My new functional is original functional plus constant distance from that set, distance of that metric space, okay? And so EJ, now EJ is a minimizer of a functional that is going to be, when I expand mu0, is going to be some perimeter, which is not p lambda, plus a volume term. Now I do have a minimizer of some perimeter plus volume term, which is going to be a strange perimeter, but still a perimeter. All right? And once you are there, you have such a minimizer. You can work with it. EJ is also going to be basically a minimizing sequence for the original problem. You do a couple of estimates. You discover that okay, now I will skip some details. EJ is a so-called quasi-minimizer of the perimeter. Quasi-minimizer of the perimeter, whatever it means. If you know, it's a bit technical. You have a quasi-minimizer because it is a minimizer of that strange problem. Being quasi-minimal implies having density estimates. That's my point, okay? Density estimate means that if you have a point here, then you have some volume there, right? And this is restoring compactness, because if you cannot have points going away to infinity, because otherwise, around those points, you would have some mass, but that mass pays by the center, basically, okay? And so this gives me density estimates, which turn EJ into an automatically compact sequence, even if I didn't have a confinement restriction. So now EJ is going to be a minimizing sequence, uniformly bounded. You are going to get your minimizer. You're going to get existence of fk minimizing fk now, automatically contained in some fixed ball for any k. Now you do have a minimizer for that problem. Since I put mu0 and not mu, also fk is going to be an almost perimeter minimizer for some perimeter which is anisotropic and actually even weighted depending on k, but at least not on the set, because I put mu0 and not mu, okay? So it's going to be a weighted anisotropic almost minimizer, perimeter minimizer, but this is enough to apply the very nice work by De Filippis and Maggi, Maggi from 15, which tells me, okay, even in this class of perimeters, then L1 convergence can be turned into C1 convergence. So you end up, as before, with a sequence of sets going in L1 to the bubble, because when K disappears, the only minimizer for that is the standard bubble. You're going into C1 there, and still you are contradicting. You get a contradiction when you pass to the limit. Yeah. For the perimeter, for the standard perimeter in H+, for the standard perimeter in H+, quasi-minimal is a very weak assumption. You just can estimate everything, so you can end up, you could do also for P lambda if you want, but why not estimating everything? You get that perimeter of EJ, you know, inside a little ball intersection with H+. This is less than, the definition is 1 plus possibly huge constant, so a very weak notion, perimeter of a perturbation G into BR intersection H+, as long as G and EJ are different inside that little ball BR. Exactly. So very weak, but enough to prove density estimates. Yeah. What it means? Okay. Almost this means. It means the following. This is more standard. PFK of, in this case, FK again in BR intersection H+. This is going to be 1 times PFK G perturbation G BR intersection H plus lambda bar volume G difference with Fk, okay? So the standard notion of almost minimality, but with this strange perimeter, depending on K, but not depending on Fk. All right, there is some anisotropy and weight. PFK is a weighted anisotropic perimeter, actually. It's more than anisotropic, okay? Okay, final comment, I promise. Because I would just, let's see, and you know, a posteriori, we weren't expecting that, but a posteriori, we have some advantage from this approach, because not requiring the confinement, and so proving a Fugler type inequality with barycenter and adding a barycentric penalization eventually gives you a method to prove the so-called barycentric versions of quantitative isoperimetric inequality. What is a barycentric version? A barycentric version is a version where you don't put infimum over X here, but you exactly put, instead of, in place of X naught, you put the barycenter of the set, which is stronger because you're increasing the infimum, even centering it at a known point. So it's a nice improvement, okay? There is a nice work by Chiara Gambicchia and Pratelli after Bianchi, Croce, and Hanro, where they proved the barycentric version of the classical Frankel type quantitative isoperimetric inequality, and this is basically a barycentric version of selection principle, eventually giving you both strong form of quantitative isoperimetric inequalities, but also barycentric version. So, for example, we can prove a barycentric version of our inequality, but also barycentric version, for example, of the strong inequality by Fusco-Ewing, and I hope some other applications. Thank you very much. Thank you for your attention.
How crucial is the fact that the constraint region is a half space? For instance, can you extend the result to constraint region a convex cone?
Oh, yes, we do that in the work. Yes, yeah, maybe I should tell this. Indeed, we do the very same analysis, proving the strong version for the quantitative isoperimetric inequality in convex cones, with lambda 0 in, because you don't even get the inequality and the characterization if you move lambda, okay? So relative isoperimetric problem into convex cone, we do that. The only technical assumption is that the cone has to be piecewise C2, and that is related to the application of the epsilon regularity theorem in the end. But we believe that if you had, this is a work by Edel and Lee, so we need to rely on somebody else's epsilon regularity theorem. The idea is if you had a better epsilon regularity theorem, you could run the same proof and you get the inequality on the class of cone where you have the regularity theorem. Yeah. So yeah, we do that.
Can you also consider an isotropic perimeter there?
That's a good question. Possibly, but I would. Oh, yeah, sorry.
No, since there is this result by...
Indeed. So possibly you can consider anisotropic perimeters where the anisotropy is convex, C2 smooth enough. Okay, but for general anisotropies, I don't know, because you don't even have the strong form of quantitative inequality in general in the free space. So right, that is an open problem. So for regular anisotropies, I would say possibly yes, but for general anisotropies, not clear.
How do you choose lambda in this?
Okay, capital lambda.
Yeah, like there is natural choice.
Here, this capital lambda here. Okay, it is a bit implicit actually. For sure, you need capital lambda greater than the dimension n, but this is just technical, because it is for that threshold, that for capital lambda greater than n, that if you erase, so when you send k to infinity, you imagine you are deleting the oscillation term. It is just for lambda greater than n that then the unique minimizer is the bubble, okay? So greater than n. But then, you know, in the proof, maybe many times you say, okay, for this estimate, take lambda even a bit larger depending on dimension and the little lambda. And so you have many improvements, but for sure greater than n. So you have a couple of choices for that, depending on what you want to do. For example, if you increase capital lambda even more, what you can prove is that the volume constraint is so strong that fk, even if k is not sent to plus infinity, already has exactly the volume equal to b lambda, for example. Not just close, but exactly to b lambda. This is convenient. So maybe you take lambda even larger, so you have volume equal to b lambda. So to do these kind of choices, you increase capital lambda.
So thank you very much.
Thanks to you.
So next isoperimetric talk given by Francesco Nobili from Pisa, and it's going to be about isoperimetric planar tilings with unequal cells. Please.
Okay, so thank you for introduction and organizer for putting up this nice workshop. So today we speak about joint work with Matteo Novara and Emanuele Paolini. This is a very Pisan project, and will be about isoperimetric planar tilings with unequal cells. So the point here is to advertise and propose a novel geometric variational problem. And I guess I owe you some motivation to begin with. So the driving question for this talk would be this informal question. So we will be asking what's the best way to subdivide the space, and I will be really interested in the plane, with a prescribed number of sets, and let me add possibly unequal. So this kind of question you can say you can be interested from a theoretical viewpoint in discrete topology and geometry. For instance, if you have concern with the packing problems. And more in line of this workshop, if you're interested in isoperimetric problems, you will be attacking this question in the realm of calculus of variation geometric analysis. However, there is also some motivational examples in applications and mathematical applications in the study of crystals, material science, and quantum systems in statistical physics. So let me be clear about how I will interpret these words, these underlined words in this talk. So for me, best would be according to the lowest perimeter sense. When I say subdivide, I'm thinking about periodic planar tilings. And when I say prescribed sets, I'm thinking of an area constraint. So it's literally an isoperimetric type of problem. And the driving example is the so-called honeycomb. So there is this problem which is called Kelvin problem in geometry. And in the plane, it goes under the name of honeycomb conjecture. And essentially, he asks these kind of questions, and I have to say, without enforcing periodicity. So it's even more general and more difficult question. And the solution was found by Hales is the so-called honeycomb tiling. So this is a tiling, but not in the among competitors which are periodic, while in this talk we will be really confined to periodic competitors. So let me add an extra word about this, why I'm considering unequal sets. So for instance, if you're interested in quantitative stability statements, as Marco was, for instance, so there is this work by Carroccia and Maggi, where it's very natural to allow unequal sets in the analysis. So when you find the stability of this configuration, and you ask how an almost optical configuration looks like, then you would naturally allow unequal sets, unequal chambers in this in your candidates optimizing. Okay, so give you some motivation. So this would be the talk. I will start with introducing the isoperimetric problem for tilings. So this will be the first part, and then I will go through results. So second part will be a little bit theoretical, but I will skip proof. So it will be about existence and regularity questions. So these are kind of the first set of questions you have when you have an isoperimetric problem. And then I will go to classification results, and here there are wonderful pictures by Emanuele Polini. So we discuss explicitly our candidate optimizers, so isoperimetric configurations and isoperimetric profile. So I will be interested in this analysis from an explicit viewpoint. And then I will conclude by saying some open questions and partial results we have. Okay. So what is a tiling? A tiling is you give me an integer n greater than or equal than 1, and the periodic n tiling is a collection of measurable sets of the plane, even though at this point you could be or in Rn or even in some manifold configurations. And there will be a collection of measurable sets which essentially are formed by n different generators, sets EI, and translating copy of that. And translation will be achieved by the action of a group, discrete group, lattice, in fact. And the condition of the defining condition of a tiling is that all these generators, when you move them, do not overlap in a negligible sense, and they cover all the plane. So this will be a tiling, and when I want to stress which is related to the lattice, and not just say vaguely periodic, I will say that this is an n tiling related to the lattice G. Okay, so so when I say lattice, I think about, for instance, two independent vectors, G1 and G2, and any other element of this will be achieved by an integer linear combination of these special vectors. And the area is canonically associated to these two vectors as the area of the parallelogram spanned by the vectors. Okay. So there is this set D is called fundamental domain. It's a special domain associated to the lattice. In fact, it has the same area. Okay. So we have our configurations. We attach to them a notion of functional, a perimeter functional. And the perimeter will be 1/2, just a choice, a constant, the sum of the perimeter of each generator. So these are our choice. So as I said, up to now, essentially, the plane plays no role. You can do this in RD, for instance. You can also attach different notion of perimeters, so anisotropic or no-local ones. And I will mention something at some point in the literature. So what is and then an isoperimetric tiling? So this is our definition. So you take an n tiling, which is relative to G, and I will call it isoperimetric relative to G, provided the perimeter increase when you consider any other possible n tiling T prime, which is relative to the same lattice, and for which the area is constrained. So each generator should of the tiling T prime should match the area of the generator of the original tiling. I have a second notion of isoperimetric tiling. Here I'm not specifying relative to any lattice, and the reason is that I'm requiring this condition to hold for any possible lattices T prime relative to any possible tiling T prime relative to any possible lattice G prime. Of course, G prime needs to have as well some area constraint, and I will be asking that the sum of overall areas will be say, a constraint for the varying lattice. Okay. So what's then the isoperimetric problem? We have all the tools. Now we somewhat reverse the question. So we fix some n-poles of non-negative area vectors, V1 up to Vn. You fix a lattice G, and you constrain the area of G to be the sum of these areas. And then you ask existent questions, so whether isoperimetric n tilings related to the fixed lattice exist, or isoperimetric in a sense relative to any lattice. So we ask regularity questions. So what can we say about isoperimetric tilings? And also classification results. So in some cases, at least, how do they look like, essentially? For instance, in the case n equal to 1 and 2, which are, I guess, intuitively more easier. Okay, so to start with some related literature. Of course, the honeycomb conjecture. So in a sense, that the structure was a one tiling in my axiomatization. But actually, it's as I said, it's even more regular. It's even more, say, minimal. You don't need to enforce periodicity. Then there are some related literature around isoperimetric fundamental domains in manifold settings, and also in RD with different notions of anisotropic or non-local perimeters in this nice series of works. Actually, there is also some physics literature which is related to the our notion of tilings, and this goes under the name of bipartite tilings with minimal interfaces. In this series of work, there were some computational analysis where there were some candidate minimizer which looks like similar to what we will be seeing next. And essentially, they were ranking the cost via computations, via numerical computations. A huge motivation also, and for the literature to mention, is the so-called K-bubble problem in the theory of clusters. So I guess this was probably introduced in the first talk of this workshop. Here I just recommend Frank Morgan's book with all the details. Okay, so let's move to results, and let's start by just saying basic existence and regularity theorems. So these are our first results. So just really standard existence theorem. Essentially, as I said, when you fix areas, you fix a lattice and you constrain the area of the lattice, then you have minimizers. So we can show existence of isoperimetric n tiling relative to the lattice. And as well, when you further minimize among all lattices with the area constraints, then we have isoperimetric n tilings. So this is a standard application of direct method where you have to couple a concentration compactness step. So in a sense, you consider minimizing sequence going in both cases going toward the same infimum. And of course, there is no L1 compactness at all because these problems are G invariant essentially. So there is no hope to get compactness at this level. But you restore it. So you plug in a concentration compactness argument essentially by restoring L1 compactness through translations. And of course, the perimeter is G invariant with respect to these actions. So the new sequence of tilings that you're cooking up will be, again, optimizing, and then lower continuity gives you the optimality at the end. Okay. So what about regularity? Here I'm fixing, again, a lattice G, and I will consider an isoperimetric n tiling related to this lattice that now it's not an empty set. And for each I, for each generator, we can prove that there exists always an open and bounded representative, so basic regularity information. And from now on, when I consider an isoperimetric n tiling, and I'm saying consider EI, I will always consider, without saying about representative, that I'm considering this one. Then there is essentially smoothness, and this is planar regularity. So these sets are regular in the sense that there are a finite number of connected components, and the topological boundary is composed by a finite number of either straight line segments or circular arcs. And I will call these edges. And then the last conclusion is that all edges must meet the triple points with angles of 120 degrees. Okay, so if you know about planar regularity theory for cluster in geometric measure theory and cluster theory, then you actually recognize all of this information. So this is not what I would like to tell you about. It's more like how to bridge from our setting to the regularity theory, which is, of course, available in the literature. And in particular, we will be using the regularity theory for minimizing clusters in the plane. So the key obstacle that makes this theorem non-trivial is that this application is not for free, essentially. The application of this regularity theory is not for free because you don't know a priori whether the partition of the plane which is induced by the tiling is locally finite. So this is the key point of this proof. And in fact, if you take any ball and you count the number of indices and translation which do hit the ball in a positive sense, measured sense, then a priori this is possibly countable, this cardinality. And you cannot apply for free regularity theory. The key point is that we are also using the two-dimensional setting to prove local finiteness. So this is what makes the regularity theory accessible for us. Okay, so this was the main theoretical part. Now we go to pictures and classification results. So we want to classify isoperimetric tilings with two different generators. So I'm considering double tilings from now on in the plane. And so I want to classify them. I want to give an explicit description. And let me start with remarks. So the key remark is that the hexagons will play a major role in this analysis. And for instance, you can start discussing some kind of borderline cases. So for instance, if the tiling is degenerate in the sense that one of the two generators is negligible, so this will be an isoperimetric fundamental domain according to my axiomatization. Well, it turns out that essentially from regularity theory, the generators must be an hexagon, which of course is not regular, should be compatible with the lattice. And this would be the picture. Another borderline case will be so whether the two generators has the same amount of area, so 1/2 of the lattice. And a good guess here is that this picture still applies with the caveat that the lattice now is the rectangle. It's not anymore the square. And the hexagons will tile the plane accordingly with the same area. So this is a good guess. The only point is that there should be something in the middle because these situations are quite far and there is a whole range of area ratio in the middle. And this is our theorem, essentially. These are our classification results. We found 3 different configurations, essentially. So you take a non-degenerate isoperimetric 2 tiling, which is related to a axis G. And then we improve, building upon the regularity theory, that the two generators are curvilinear polygons with angles of 120 degrees. And upon exchanging the two, we have essentially 3 possibilities. So at least one of these will be in place. So what I will call configuration 3-9, which is this picture. By the way, in this picture, the lattice is different. I just select a lattice so that the picture is more pleasant. So the 3-9 will be an hexagon which is chipped, and you put on a tiny Rayleigh triangle, which is a curvilinear triangle with the correct angles on a vertex. And you should suspect these to be the minimizers, because this is asymptotically optimal, and in the sense that it goes to the hexagon, to one hexagon when the volume of the triangle shrinks and has all the correct regularity constraint. So in the middle, there is this third wheel. This was quite painful to analyze. So this will be a strictly convex curvilinear quadrangle with rectangular symmetries, and the other set E2 would be a chipped, this would be the chipped polygonal, and the red one would be the convex curvilinear quadrangle with these rectangular symmetries. And the last one is configuration 6-6. As I said, this regime of area allows to have two hexagons which are sharing a flat edge. Yeah. So if you want to visualize the tiling, this would be the picture. So of course, the lattice are different here, as I said, but this would be the tiling in the plane. Okay, so we have a basic classification results. I want to point out that we don't know if you give me a lattice and the tiling, and if you give me a lattice and, for instance, two sets of areas, we don't know whether all of them could be actually isoperimetric. The classification results just tells you that one of these at least one of these holds, essentially. And we suspect that there are some cases where just two of them holds. So this truly depends on the lattice, essentially. And of course, and also we don't have the explicit value of the cost with respect to the lattice. So the computation are quite implicit. So the point here is, from now on, is okay, let's further minimize among all possible lattices then. And the hope and the reason is that maybe you will select some more symmetric configurations, and computation will be way more accessible, and we can reach an explicit description. So this will be our goals now. And let me rephrase these goals by means of isoperimetric profile functions. So I fix a lattice G with area 1 for just by scaling, this is enough. And the isoperimetric profile function, which is relative to lattice G, will be essentially the cost of the isoperimetric double tiling with this relative to the lattice G when I assign area x and 1 minus x to the generators. I will call this IG of x. And then when I further minimize among all lattices with area 1, I will call just I of x. So the point is now to give an explicit description of this problem and of this profile. And in fact, I want to compute I of x. I want to know minimizers, and for instance, uniqueness of them. And I want to discuss the lattice, and I want to discuss phase transition. So we have these three possible classification results. I want to exactly know in which sequence they appear, and what are phase transition points. So this will be our theorem. The formal theorem is the following. So we have 2 points, explicit, x1 and x2, which will be between 0 and 1/2. And the profile is essentially piecewise graphical between those points, and is symmetric around 1/2. Okay, in particular, you have concavity information. So, so this looks a little bit, you have to guess what's behind. So this is really what's happening in this piecewise graph. I want to essentially discuss it with a picture and then come back. So we start at 0, area 0, tiling degenerate. We know that there is an hexagon here, the regular hexagon, because I also minimizing among all possible lattices. And then you start a Rayleigh triangle starts to appear at the vertex until the point x1. At x1, we have 2 optimizing configuration, and this is the first transition. So we pass to the second object, which is now very symmetric. It's like a chipped squared, and then you have a curvilinear quadrangle at the vertex. And from x1 on, this starts to be more convenient, essentially. And this goes up to x2, where you have a second phase transition, and now you start seeing you start seeing hexagons again, and you can convince yourself that from x2 to 1/2 the cost is constant, just because you can move these flat edges a little bit, you exchange the area, and you don't modify at all the perimeter. And this is more convenient than the other. So these are trigonometric computations. Of course, it would be symmetric around 1/2, and this is exactly what's written here, what I discussed in words and the picture. And just one comment: unless you are at the phase transition points, the tiling is uniquely determined up to isometries. So of course, for instance, translation of the lattice. Okay. So this would be the picture. So this is how the tiling look like. So again, we also explicitly have the information around the lattice, G of x, which is here is the one of the honeycomb. Here is just a square lattice, and this would be a rectangular lattice. And of course, you can yeah, and then you can. These are 3 random points essentially in these parts of the x-axis. Okay, so okay, let me go. Sorry, a little bit. Let me go through open problems and discuss some other partial results. Okay, so the first thing is what happens with when you increase the number of n, so of the generators. And ideally, one can ask whether we can classify, at least in some cases, isoperimetric n tilings with the bigger n now. So we have a qualitative partial answer in the almost equal areas regime. Let me say that actually this was the motivation of the explicit analysis in the first place. So this theorem here, we actually deduced it before. I think it's nicer now to present it at the end, actually. So this is our first motivation to analyze the lower, say, n case. But now it's really something in the direction of an open problem. So this would be a qualitative statement. So for every integer n, we know that there exists a non-explicit delta parameter, which is between 0 and 1/2, such that if you take any n tuples of vectors, v1 up to vn, and you require, so this is the almost equal areas regime, you require each vi to be close enough to 1, and I'm thinking all the vectors to sum up to n, and I'm looking at lattices now with area n. Then if you look at the cost of the isoperimetric n tiling with this vi area constraint, then we know that the cost is n/2 the perimeter of a regular hexagons of area 1. So I'm saying this is really a qualitative partial answer to this question, and the reason is that we exactly know how to achieve this cost. And you can achieve it by essentially stacking n different hexagons, and now you tilt the edges in order to match the area. So you start essentially with n different regular hexagons, and then you attach each of them to a flat edge, and then you tilt in order to match the area. And this has precisely this cost. So this would be your candidate essentially minimizer. And how do we, and some remarks. So this, of course, via suitable lattice G, this tiling induced by this set CI would have this cost. So this is a competitor, as I said. And you can recast, in a sense, this theorem as a qualitative stability statement for the honeycomb conjecture. Of course, among tilings enclosing unequal areas. So it's not really the full honeycomb conjecture. But it's, in a sense, a qualitative statement attached to that configuration. And let me give you a word about this. So of course, this statement is qualitative. So we have no information about how close this area should be to 1. In fact, it goes by contradiction. So you start by contradiction, you end up with a sequence of sets. They will eventually have closer and closer area to 1. and you have to combine essentially now a compactness step with the stability of the honeycomb, so of networks, to found this into the independent works. Okay, so this would be the first. Then you have a second set of open problems. So as I said, we have some basic information about isoperimetric entangling relative to a lattice G. However, we have like all of the analysis is quite implicit, so we cannot really say whether, for instance, given a lattice of G with area 1, so for instance, for which point X, the configuration 4-8 is admissible. So remember the intermediate one, which was made by rectangular curvilinear polygon with a chipped octagon. So we have no idea, given lattice G in general, so with the dependence of the lattice and the point where this pops out, even is admissible. And also we don't know subsequently when it will be for those axes, which axis for which is admissible gives you also that is convenient for the cost. And the last set of questions is, of course, what is the precise value of the isoperimetric profile function relative to lattice G, at whether we can explicitly give a phase transition point description. So in a sense, you can interpret this kind of open problem in two ways. So one, maybe rough numerically. So you just try to run numerical computation and try to, in a sense, address the first two. And then the last one would be easy at that point, because we have implicit description of this cost, just that is not explicit, analytic. Or the second way you can interpret this problem is that maybe you have your favorite lattice G, which is interesting for, I don't know, materials or your application. And then with that lattice, you address this, and then you try to do it explicitly. So this would be maybe more interesting, at least for our analysis. And also there is a kind of non-periodic scenario. So I remember that, I'm saying that the honeycomb was, say, optimal, but even if without enforcing periodicity, in fact, it's a local perimeter minimizer. And we actually do have partitions. So our candidate, our isoperimetric two tilings are tiling the space. So there are partition of sets of polarimeter, and they're periodic. And you can essentially ask the Kelvin problem with two cells, so whether these are local perimeter minimizers. And this is not clear in the sense that in some range of area, this cannot be possible. So there is a natural guess of a better minimizer, essentially, in this, of course, in this sense. And but it's completely open whether in the other ranges this is actually the case. So this would be more interesting. This is very interesting. And I think I was quite fast, but okay, this was this last day. So these are our references, and I encourage you to scan this and go to the Polynese app, where you can play with these tiling configurations. And I stop here. Thank you for your attention.
So, thank you very much for the presentation. We have time for some discussion. Are there questions?
Actually, I have a couple of questions. So first, I would like to know if your result about existence is also possible to be proven in surfaces. So if the ambient is not the plane, but
Okay.
Riemannian metric.
So I think what we rely on is a concentration compactness tool in a paper by Novaga, Paolini, and Tortorelli, which I think is quite general. So it's like in homogeneous spaces. So I guess as soon as you have a surface, and then you have a proper notion of translation, so a group action, then it should be possible. Maybe you're saying with the classical notion of, I don't know, perimeter length, maybe in the two-dimensional case. So this should be, of course, you have to take all the, you have to really have a group action there. So translations. This should be okay, existence.
And the second question, if you have a metric that is close to the one of a plane, if you are able to prove a perturbative result, saying that your classification more or less remain true if you are very close to the flat metric.
You mean in the other area regime, I would say. Just have an idea. So so say it again, your
Well, it's a bit vague. Suppose that you have a metric that is close to the flat metric.
okay, so
and-
perturbative in the sense
yeah.
of essentially the distance of your ambient space. So you're saying maybe
You still have some
so you're
object
thinking
that-
about like anisotropic versions. So you want to
Well,
different,
was
not
more
Euclidean
vague. The
distance.
question was not so precise. So several directions.
Okay, so for instance, if you want so if you want to allow anisotropic so non-Euclidean distance, and therefore you compute perimeter with respect to other kind of distance, we have regularity information actually. Yes, but not classification result. There actually also there is some conjecture here. At least, for instance, for the L infinity, for the how it's called the L infinity norm, I would say. So well, yeah. These are squares, and there is also a related Honeycomb conjecture for the L1, say L1 distance or L infinity dual. Yeah, there are natural candidates there in the two Tilings sets for every area regime. So we have some guesses there, but we like the proof. So
Very good. Anything else? Everyone is looking for coffee? You have something? No. Okay.
yeah.
Yes.
Maybe you said it and I don't remember it, but so do you know if for any lattice there exists an epsilon such that for x less than epsilon you have the first configuration? Like not compute.
No, actually, we don't know.
Not even
We
that.
don't. I mean, it's quite natural, of course. So for sure, it's not written in the article. Let me think if it's quite fast. I don't think it's fast because I mean, if you want to a qualitative statement, you would converge L1 and then I don't know. I don't think. So I guess it depends whether with the fixed lattice the hexagon, distorted hexagons, which are tiling the space with area 1, say, are stable perimeter minimizer. I think this is the only point that I would need. Probably this is the only point. Yeah.
Thank you.